Okay, it's 9 o'clock. So let me check your attendance. 박건호 씨, 정상묵 씨, 한성민 씨. So if you are here, then please leave a message in chatting log. Then I can see your attendance. Okay. 한성민 씨 안녕하세요. 네, 박건호 씨 안녕하세요. 네, 정상묵 씨 안녕하세요. Okay, so this course is the computational microelectronics course. The code number is, I guess, EC 7114. So we have three enrolled students in this semester, and all from my laboratory. So we will have a really more intense course to give you more information. So let's get started. So I will just make a public live streaming, but I think that maybe there will be just 3 students who are actually watching this live streaming. Okay, so okay, before starting our entire semester, I wanted to say to our enrolled students, so Mr. Han, Mr. Park, and Mr. Jong, so please try to ask me questions. So that is the very first rule we have to keep in mind in this course. So you know, as I will explain soon after, actually lecture material is already available to you. So if you are willing to find something, actually you can find many resources from our recorded YouTube lectures and GitHub repository. So point is not repeating my live explanation again and again. So that is just a waste of time. So if you have questions, answering to your question is more valuable to me. So please feel free and ask me whenever you have questions. Okay, so that is my first rule in this course. And you know, in this course, since this is the course in its 7000 series, so we will not have any kind of midterm examination. So no, and we will not have a final examination. No, no written examination will be given to you. Instead of that, you will have the final presentation. So final presentation will not be a live one, so you can just submit your recorded presentation, and based upon the quality of the final presentation, I will give you some weighting factors or some scores to you. And of course, usually I check your attendance, but I hope that actually all of you will attend quite regularly. So I'm not afraid about your attendance. So attendance in this semester will not be counted. So of course I will count the will check your attendance, but I think that does not make any difference between you. And another one is homework. So we will have lots of homework. Almost every lecture we will have homework. So please try to finish your homework within time. And if that happens, then maybe it will be very easy to prepare your final presentation. Okay, so this is all about the lecture progress, and um, Tuesday and Thursday morning 9 o'clock, please join my live streaming. So that's for your lecture attendance. Okay, do you have any question? So Mr. Han, Mr. Park, and Mr. Jong, if you have any question, then please let me know. And if you don't have any question, then also leave that. You don't have any question right now. Yes, please respond all our three students. Okay, Mr. Han, you don't have a question now. And how about okay, Mr. Jong? Okay. Okay, yes, thank you for your good question. So I'm trying to give the in-person lecture. So that is the the my hope to give you or meet you in a classroom. So let's cross fingers to have such an opportunity. But well, I'm not quite sure about that. So let's just hope that to have the offline or in-person lecture. Okay, thank you. And it really depends on the schools or universities regulation. So if the mm, the university allows me, then I will immediately start the offline lecture, and the offline lecture will be exactly same with this one. So in this semester, I'm trying to just copy the environment or atmosphere of my offline lecture through the YouTube live streaming. So I do not provide you the PowerPoint file, because usually in my lecture, offline lecture, I just write down in my blackboard. So yes, that is the reason why you must find out some related material from our previous GitHub repository. Okay, thank you for your question, Mr. Park. And do you have any further question? So also other students can ask me whenever you have related questions. So it's free to give me questions. Okay, then if you don't have any questions, then I can just introduce our GitHub repository devoted to this course. Okay, can you see it clearly? Yes. So just following our convention. Oh, let me just magnify. Uh, magnify. Okay. I hope that it is much better for you to watch the screen. Okay, here you can find my new repository CM2022 as you know it. So it's Computational Microelectronics 2022 this year and spring semester. And here I have made three folders or directories for each of you. So this is for Mr. Han, and this is for Mr. Jung, and this is for Mr. Park. So when I just click one of them, then there is nothing. So this is nothing only because you have to fill it. I mean that for each of you, I will give you the homework problem. Then please make the homework or upload the homework in your designed repository. For example, let's say we have homework number 1. So n due is something, then I will give you some write privilege, so you can later upload your files in this repository. So in this case, for example, if you have to upload your files, then for example, in the case of Mr. Han, in this case, go to this add file, and you wanted to make a new subdirectory because you know this is the top directory for Mr. Han, and if Mr. Han just dump his all homework problems into just a single directory, then it will be just full of files, so nobody likes it. So I just recommend you to make a new file, and when you click new file, then you can say your desired name for subdirectory. For example, homework 1. Oh, sorry about that. Homework 1, and always try to add readme.md. So this is the explanation for directory and homework number 1. So just a simple remark is enough. So this is not the most important part of your homework. This is just to make some spaces for your homework number 1. So it is not allowed to have an empty directory in GitHub. So if you wanted to have any directory, then you have to add one at least one file. So there is no way to generate directory directly. So directory is always generated by adding certain files into certain position. Then it automatically generates file structure. Okay, so when we just make it, then commit, then you will have something like this. Then let's go to the top stage. Then we can still can see Han Jung Park, and when I click Han, yes, now we have a newly generated directory whose name is just exactly same as I wrote. So when I click it, then here you can see that readme.md file is here, and when you have your real files like report file or code file, blah blah blah, then you can just upload it in this part. Okay, if you have another homework, for example homework number 2, then following the exactly same way you can add many things into it. Of course, this is possible because I have made this repository, so you don't have the right to uh, to upload certain files, but don't be afraid. So I will give you some right permission, then you will later can upload your files. Okay, so do you have any question about this use of GitHub repository? Okay, No. Okay, so then let me just announce our first homework like this. So I will make a new file, just like a home work. Okay, then of course I have to make a readme.md, a directory for homework problems. Okay, then I made a homework directory, and I will announce the homework number one. Homework number one. Okay, so this is a new file. Yes, so homework number one. What did you do? Due is so let me just check next Tuesday. So March 8th, March 8th, 2022, and AM 8 o'clock. So just 1 hour before our next lecture starts. So we have only one single problem. So solve the Laplace equation for a 1D structure. So usually so that it is not the very first example or exercise in our introduction, our book, Introduction to Computational Microelectronics. However, since all of you have some previous experience on the numerical calculation, so I just wanted to skip some unnecessary steps to ramp up your numerical calculation skill. So I will assume that you have all of you have some capability to write your own code. So let's just directly jump into the main topic. So solve the Laplace equations for 1D structure. Then obviously you are curious about the length of your system. So just given by certain parameters. So you can set it, and also boundary conditions. Boundary conditions. Yes. So also you can specify the values at the left boundary and the value at right boundary should be given by the users. So user can specify the length L and left boundary and round boundary. So supplied by users, and also it is supplied by users. And boundary condition, this is directly boundary conditions at both ends. Here both ends means that leftmost position and rightmost position, you have to specify the value of your function. So now you will have the complete system to be solved. Okay, then how about the discretization? So you have to also have something like this, but point is now mesh. So please invent a clever way to build a mesh. Okay, so what is this? What is the invention of a clever way to build a mesh? For example, if you just allow uniformly discretized mesh, then actually it will be enough to just introduce a number, one single number. For example, 100 means that you just divide your length L into 100 pieces, so small intervals, which is 100th of the total length L, then everything will be uniformly distributed. But here, when I say mesh, so you should be able to consider non-equidistant grid point, non-equidistant grid point. Okay, so can you understand my pose? So usually in the book, so in the introduction to computational microelectronics, I always prefer to have an exercise with equidistance grid points. So in that case, everything is perfectly uniform. However, that is actually idealized case. So in many cases, we have to have non-equidistant grid points. So you have to find out a way to build a mesh with certain non-equidistant grid points, and the way to specify it should be invented by you. So please think and invent. So I will not introduce any specific way. So there can be many different ways. So the purpose of this one is now you are developers. So you have some freedom to build your own code, and in your code you can have certain choices to build in this way or that way. So not all of your choices will be the best one. So sometimes you will make a bad decision, and sometimes you can make a good decision, but that doesn't matter. This is just educational purpose. So please think your own way to make a clever way to build a non-equidistant grid points. Okay, so I just commit new file, and now you have the homework number 1. So maybe you have 5 days. So please try to do your homework number 1. And I don't care about your development environment. So for example, some of you can use MATLAB, some of you can use Python, and some of you can use C or C++, whatever. Anything is really good. And but point is, please think that since you will spend quite a long time on these homework problems, so I think that maybe during your master degree course, maybe it is quite possible to build your own masterwork based upon this code environment. So when you use a certain thing, then please think that this is not for only for this course, but it's for your entire 2 years or 1.5 years for the master program. Okay, so do you have any question up to now about GitHub repository and homework number 1 just announced? So if you have a question, please let me know, and if you don't, then please you leave your message. So I don't have any further question on this aspect. Okay, good. So then I think that okay. So oh okay, Mr. Park, thank you for your good questions. But you know, Laplace equation is not a specific, uh, not an equation specific to the material. So that is a really good question. So let me just start our. Yes, thank you for your question. So that is quite a reasonable question. So let's say that our solution function is called as, for example, phi. Then what is the Laplace equation in its general form? So it is just written as this. Yes. So in this Laplace equation, we don't have any parameters which depends on the material property. For example, if we consider later certain equation called Poisson equation, so although that is not strictly Poisson equation, but we have certain equation like this. So this is actually Gauss law. No. However, by introducing certain approximation about the displacement vector, so like this, we can have this form. Okay, epsilon, and epsilon is permittivity, and permittivity can be a function of position. Yes, and we have this kind of equation. In this case, it is certain that the permittivity is a function of a position, but that is sometimes that is not direct function of a position. It is sometimes regarded as material dependent one. For example, if we have a combination of silicon and silicon dioxide, if R is belonging to the silicon region, then that will have the permittivity of silicon. And if R is belonging to the region of oxide, then we will use the oxide permittivity for epsilon. So in this case, it means that the Poisson equation, so-called Poisson equation, is a really material dependent equation. Yes, it's quite material dependent. However, when we come back to our Laplace equation, but in this case, you cannot find any kind of position dependent quantity. Actually, here you have just number 1, so which is universal everywhere. So you don't have any material dependency. So don't worry about the material dependency. And yes, I think that that can be a good answer to your question, Mr. Park. And it was a really good question which can be raised by newcomers. Okay, so Mr. Bak, how about your opinion? So are you satisfied with my answer? Or if you have further questions, please let me know. And other two students, Mr. Han, Mr. Jung, if you have a question, please let me know. Okay, so now Mr. Park, gave a good question to me. So accidentally we have introduced the Laplace equation, and of course we will use the Laplace equation as a starting point for implementation of Poisson solver. However, for a while we will just concentrate on the Laplace equation solver. Okay, so now we have a Laplace equation, and since I'm asking you to just build 1D variant of the Laplace solver, then in this case you can make a simplification. For example, usually this Laplacian operator should be regarded as, for example, this one, second derivative with respect to x and with respect to y and with respect to z direction. Okay, that is the general form in three-dimensional space. However, since we have introduced 1D approximation, so this one and this one will gone, then will be gone, and we will have just a simple relation like second derivative of our solution function, or our unknown function phi should vanish. So that is the Laplace equation in one-dimensional space. So then in this 1D approximation, then what you can do is to integrate the Laplace equation. So this is Laplace equation in 1D space, and this 1D space Laplace equation is integrated. So let's just integrate, and here we have a certain lower bound, and here we have a certain upper bound, and this is just integrate. Okay, so I just pause a little bit while because my OBS Studio experiences some problems for a while. So can you hear me clearly? So I'm afraid that you are lost, or your connection is lost, or I am lost. So if you can hear me, then please let me know. So maybe some interruption occurred during my live streaming. So could you please leave your message if you, oh, okay, good, thank you. Now my OBS studio was disconnected for a while. Okay, so let's continue our discussion. So we have Laplace equation in 1D space, and we have integrated the equation itself for certain range. So certain range here starting from xl and ends at xu. How can you set these two values? That will be the topic of our discussion later. But for a while, just to say that that is given numbers. Then obviously this right hand side is still 0, because when we integrated our 0 over certain range, then that is identically 0, so no problem to have vanishing right hand side. Okay, so now we find that this is, oh, I made a mistake here. Oh, there is a missing integral dx here. Oh, sorry about that. dx. And since it is the derivative of first derivative d over dx over d phi over dx and dx, you know it quite well. So by integrating it over certain range, then you can easily understand the result of this integration will be, so d phi over dx evaluated at xu upper bound minus d phi over dx evaluated at xl point should vanish. This is the Laplace equation integrated over certain range. Okay, so I hope that everybody can understand this one quite easily. Then the remaining thing is, now if we can express this first derivative at certain position xu and first derivative at certain position xl, then everything can be done with our discretization. So when we think about this expression, so how can we express this first derivative and first derivative? These first derivatives should be expressed as certain unknown function values. Okay, so here, because we wanted to know the values at x phi at sorry about that, instead of this general expression using r, then I can just write down x1, x2, x3, blah blah blah. So we can have a certain function values at certain point. So then we must express our first derivatives and another first derivative using our function values at certain position. Then natural question is, how can we set this x1, x2, x3 and x4? You know it. If we have a domain starting from x equal to 0 and the right end is x equal to n, then usually we wanted to introduce a certain point inside the domain. Of course, it is preferred to have the left boundary and right boundary. So you can easily understand at least these 2 points are required to describe the boundary or the end of our simulation domain. They are understood. And how about introduce more points inside our simulation domain? That is a good idea. For example, if we can introduce a point in midpoint, yes, that will give us more detailed information. Or if we introduce more point here, okay, that will also introduce more information. Yes, so let's say that now you have something like this. Okay, quite beautiful and pretty. So they have equidistance. Yes, yes, they are all equidistant. Then you know that that will be quite easy to describe or discretize. So since that is already given to our book and lecture materials and something like that, I will not talk about this one. But think about this example. Yes, I will show you certain example about the reason why we need non-equidistant mesh. For example, think about this one. Yes, and yes, and this is our x-axis, and let's say that we now have a p-n junction. p-n junction, and let's say that this is doping density. Yes, and this is a doping density, and positively charged dopant, ionized dopant, is written as positive one, and negatively charged one, so p-type dopants, are written as negative one, and happen to be here we have exactly at midpoint x equal to half of L, and that point is happen to be the metallurgical junction point. Then what will happen to our system? For example, yes, here we have donors, and yes, here we have acceptors. Then you know the solution of this p-n junction system. How does it look like? So physical quantities, here physical quantities means that, for example, electrostatic potential or electron density or hole density varies quite abruptly only at this point. And this point or this range or this layer is called as depletion layer or depletion region. So here we have a very narrow region where all kinds of information varies abruptly and quite rapidly. But point is, now if we are talking about this part or talking about this part, life is much more boring and comfortable. So, in this case, we can say electrostatic potential is almost uniform over this range. And also electrostatic potential will be, or any kind of physical quantity will be almost uniform over this range. But here we have really sharp change of physical quantities. So in order to properly discretize or describe this p-n junction system, yes, we have to introduce several points in the depletion region. Okay, so it means that we have to introduce really short distance between two neighboring points. And what happened for this one, or what happened for this one? If we keep that short distance used in the depletion layer to this neutral layer in the n-type region or p-type region, then total number of discretized points or grid points will be quite high. Okay, so some of you can ask me this question. Okay, professor, I don't care about that number. So I have a powerful computer, and if I just discretize my system with, for example, 1 nanometer spacing, but usually just our PN simulated PN junction is at most 1 micrometer long. So I can spend, for example, 1000 grid point quite easily. Even in the case I have to use instead of 1 nanometer, but even in the worst case like a 0.1 nanometer spacing for entire simulation domain, 1 micrometer long, that will be just 10,000 grid points. And if we consider electron, hole, and electrostatic potential, then we will have an additional factor of 3. Okay, 30,000. That doesn't matter to me. I can afford it. So that can be a question, natural question by our students. But I wanted to stress that that is all related with one-dimensional approximation. What is your ultimate goal as a code developer? Your ultimate goal should be the development of a three-dimensional code, three-dimensional real space code. So saying 1,000 or 10,000 degree of freedom for one direction, one spatial direction is not affordable at all. So you have to minimize the number of grid points as much as possible without sacrificing your simulation accuracy. Okay, so therefore it is quite clear that we have to have non-equidistant grid point. So that is quite obvious. Okay, so do you agree with my motivation for non-equidistant grid points? So if you have a question up to now, then please let me know. So simply speaking, my answer is in order to reduce the total number of grid points, non-equidistant grid point is really unavoidable. So we have to consider that case. Okay. So please leave your question. Any question? So if you don't have a question, then say that you have no question. So then I can proceed with this non-equidistant grid points. Or if you have a question, please let me know. Okay, so then now we have to consider a general case where the distance between two neighboring points are uniform, are not uniform. So let's think about certain position. So let's say this one has a general index I. So I can be certain number, for example 75 or 86, any number. And here, since we have just a one-dimensional system, usually we will label them with some neighboring numbers like I minus 1 and xi plus 1. So I minus 1 means that that point is located just nearby left of xi, and xi plus 1 means that the nearest neighboring points, however, in the right side. So now say that this is a certain distance and this is a certain distance. Of course, that distance can be easily obtained by taking the difference. Xi plus 1 minus xi will specify the distance, and here we can specify xi minus xi minus 1. That will specify also the distance. The point is, when we consider the integrated Laplace equation, we have to evaluate the uh, the first derivative of our unknown function at upper bound and lower bound. Then how can we assign the upper bound and lower bound nearby x sub I? So one possibility is, for example, this one. How about this? In this case, let's say xl is happen to be xi minus 1, and xu upper bound is, yes, x sub I plus 1. Then if we set the upper and lower bound in this way, then we have to calculate the first derivative at xi minus 1. Okay, also we have to calculate first derivative at xi plus 1, and the difference should be 0. This is the one-dimensional Laplace equation, integrated Laplace equation evaluated around our certain position called x sub I. Then, yes, it's possible. So if we set xl and xu in that way, then obviously we can have this one. Then point is, now our goal should be find out certain expression for the first derivative of phi function. But you know that unfortunately the field or the information about available at x sub I minus 1 or x sub I plus 1 is not its first derivative, but we know it. Yes, for example, we know this one, and we know this one. Of course, we know this xi. But although we know the function value at this xi minus 1 or xi plus 1, but the first derivative, or its first derivative, it is difficult to answer. Oh, it is because, the first derivative is in principle given by, for example, if we have to evaluate this one in analytic sense, then it should be like this: xi plus 1 delta minus y xi plus 1. So this is the analytic form for our differentiation. So we have to find out two different function values. Actually, the differential operation is derivation is related with taking the small difference between two neighboring points. So although we know the value and we know the value of the function, however, it is difficult to take the difference. Then where can you find the difference? Of course, we should not take the difference between this and that. Oh, they are too far away. Or let's say that take the distance between this point and farmost point, and let's try to take the distance between these two. It is not that appealing because that does not give us an information or approximation about the derivative. So in order to give the best approximation for our derivatives, at least we have to think about the difference between two different neighbors. So possibility is most find in this difference or that difference. So their difference will be closely related to the derivative. However, if we consider the difference between x plus 100 minus x 50, maybe they do not have any relation with the derivative because they are too far away, and derivative just consider local change or local rate of change in a certain position. So if you can understand this argument, then you know that it is much more reasonable to define the derivative or approximate form of derivative not in this xi plus 1 or xi and xi minus 1, because here we have function values. In order to calculate the difference, then maybe more neutral way to define certain quantity, the difference quantity will be the midpoint and the midpoint. Another possibility is that, okay, although we take the difference between 2 points, but I will assign this difference into here. And although we have a difference between xi point and xi minus 1 point, I will define in here. It means that I have a strong preference to the more right side placed point for taking the derivative. However, why we have to prefer this right side? Why we do not prefer this more left side? It's difficult to answer. Of course, you can say that this is my decision, so I will just follow my decision. Yes, you can, but it is difficult to be justified. So instead of urging that I will use this choice or that choice, it is more reasonable to have a neutral view. Okay, instead of considering certain grid point x sub I minus 1 or xi, then usually people try to define the difference as a property of which point? Property of the midpoint. And that in this case, people try to assign the difference at xi plus 1 plus xi. This is the midpoint, and this one xi plus xi minus 1. This is the midpoint between this xi minus 1 and xi. Okay, so up to now I have explained that it is reasonable that the difference should be defined not on the grid point but the midpoint between two neighboring grid points. So, do you have any opinion on my argument or my discussion? If you have any opinion, then please let me know. So, of course, although I told you that this is quite obvious and reasonable, however, I should say that this is not the only way to discretize our system. So this is a kind of the simplest way to discretize such kind of thing. So yes, if you study further, and you can find many different ways to discretize the equation. But anyway, in our course, I will just let you know or tell you the most frequently used techniques used in the computational microelectronics. So that's the reason why I just told you that define the difference at the midpoint instead of grid points. Okay, so we have 3 students, and please respond to my question. So up to now I have discussed about the reason why we assign the difference at the midpoint. And if you don't have any further question, then please let me know. And if you have a question, also please let me know. Okay. Okay, so, but I think that this is the first lecture, and you have basic knowledge on the numerical simulation. But anyway, when you have any further question, please let me know. This is really important to ask questions. So once we accept this concept, then you can guess that this and that, that is not that much appropriate, because this grid point x sub I minus 1 or x sub I plus 1, in this case we do not define the difference. The difference is defined at midpoint, so instead of that, it seems that it is much more reasonable to define at midpoint between xi and xi plus 1, and midpoint between xi and xi minus 1. So if we define this lower point or lower bound and upper bound, then we can now say d phi over dx defined at xi plus 0.5 is approximated as phi at xi plus 1 minus phi xi divided by the difference between 2 points, so xi plus 1 minus xi. Quite similarly, we can write down in this way. So then let me just change it. The upper and lower bounds 0.5, 0.5, and d phi over dx evaluated at xi minus 0.5 is approximated as what? Phi xi minus phi xi minus 1. Yes, so you know it. This expression is still valid for uniform grid points. However, point is this is also can be applied to non-equidistant grid points. For example, if this number is large and if this number is small, then doesn't matter. So you now can consider non-equidistant grid quite easily. Then why don't we just combine them all? Then how does it look like? I think that is quite straightforward, but let me just write down in this way. Phi I plus 1, so this is a short-handed form of phi at xi plus 1. I will use this convention in this lecture, and phi I xi plus 1 minus xi minus phi I minus phi I minus 1 and xi minus xi minus 1 equal to 0. That will be, yes, this one will be once again the one-dimensional Laplace equation which is integrated over a small range or narrow range around x sub I. So you can collect similar ones for different xi positions. For example, you can try to evaluate this equation at x sub 2, x sub 3, x sub 4, and blah blah blah, and you can collect many equations and combined with your directly boundary conditions, you can build a complete set for your unknown function phi. Then now solving that matrix equation, you will get the solution. Okay, do you have any questions up to now? So today we have introduced our course. So about 30 minutes, the first 30 minutes have been spent for that introductory material. After that, we just discussed about the one-dimensional Laplace equation. And here, the main focus was the use of non-equidistant grid points. So I just gave you the motivation why we have to use them, or why we have to prepare the non-equidistant grid points over the uniform one. After that, the technique to set the upper bound and lower bound, and by taking the midpoints as upper and lower bounds, then we can have a very clear and beautiful discretized point. So by using this one, then you can have the full set. So since you are all experienced with building a matrix equation, I will not talk about it. So today I will stop here, and our next lecture will be devoted to the extension of the Laplace equation solver into two-dimensional or multi-dimensional cases. Okay, so do you have any question? So if you have a question, please let me know. And if you don't have a question, I will wrap up this course. And please remember that you have a homework, the very first homework. Then please prepare and submit your homework within the time due, and I will not allow any of delayed submission, so please keep the schedule. Okay, do you have any question? So if you know, then please leave your message, and you don't have any further question, and then I will wrap up today's lecture. Oh, okay. So we have next lecture on March 8th, but please upload your homework up to 8 o'clock in the morning. So we start our lecture at 9 o'clock, but due is 8 o'clock. Okay, so 1 hour ahead the lecture start. Okay, thank you for your question, and please upload it. Of course, when our lecture is over, then I will add you as a collaborator of our GitHub repository. So now you can add your homework. You can upload your homework. So if when I just add you as a collaborators, then please upload the test files. So whether you can generate the folders or something like that. So please do your exercise for homework submission. Okay. Any further question? So if you don't have any further question, then I wanted to wrap up today's lecture. And please remember that this activity during our spring semester will be the basis for your master program research. So please concentrate on homework programs and lecture contents. Okay, thank you for your participation, and see you next Tuesday. Bye.